So this diagram, what you see, is the spiral inductor, which is very frequently used in RF circuits. Even though its size is also big, but at least this inductor can provide a very good replacement for the actual inductors. So although the circular spiral is going to have a very high Q, many technologies are not supporting the fabrication of circular spiral inductors. So here we have a rectangular spiral inductor. So it is mostly made up of a metal, and you can see the center point. As you can see, the spiral is going to take a rectangular shape, and it is going to increase the length is going to increase in uh, periodic fashion, and across the two wires you can expect an inductive effect to take place. So the current flowing through the wire will circulate in this fashion. It will produce the magnetic field, and it will produce a necessary inductive effect which is required in our RF applications. So inductance of such spiral inductors is a function of geometry. As you know, it is more or less you will have a radius coming into picture. So the inductor formula, you see, the inductance is mu naught n square into R. Mu naught, you know, it is 4.10 power minus 7. N is going to be the number of turns, and R is going to be the radius of the spiral. So here we will not say radius. We can say it is half of your length of your rectangle. It is a square spiral here, so the length and width are going to be same 2r. The largest length, I mean, okay. The largest length is 2r, so half of that is going to be the radius of your spiral. So that comes in the formula for inductance. So 1.2 into 10 power minus 6 n square into r. So this equation typically yields numbers on the higher side within 30%. That they say that this equation has a poor tolerance and it will yield sometimes higher numbers, but actual value of L present in the circuit will be very less in numerical value. That is what they say in this equation. Other than square spiral, what all for whatever shape you consider, you have to multiply the value given by square spiral by the square root of area to obtain the crude estimate. So square spiral is going to be the reference for us. So whatever other model you are going to have, you just multiply the inductance value by the square root of the area ratio to obtain the estimate of that model. Actual inductance, you have to pass current through that, and you have to measure the voltage, and you have to find out the actual value of L. So what is the estimate of L? You can just find mathematically by multiplying the inductance of square spiral by the square root of area. Okay. So for circular spiral, you have to multiply the square spiral value by 0.89, and for octagonal spiral, you have to multiply by 0.91. Approximately, you can say it is 1.89 and 0.91. You can say they are approximately having the same inductance value, but lesser than the square spiral. So the most approximate value is going to be this. The equation is this one. N is approximately equal to PL by mu naught power 1 by 3. You know N is the number of turns. So if you want to find the number of turns, you can use this formula. You know P is the pitch, winding pitch, and mu naught, you know, it is the permeability of free space, and L is going to be the length of the inductor. So this formula you can use to find out how many turns you require for an inductor. Uh, so if you want to manufacture 120 nanohenry inductor, they have said that you need to have 27 turns. So the spiral, whatever thing you have to have 27 turns. So one turn is this one. This is second. This is third. This is fourth, and this is fifth. So like that, you have to have 27 turns if you are going to have a square spiral, and the area will be 140 micrometers. You know, it is fabricated in a on a small chip. So the diagram what you see is actually magnified, but actually it will be coming under 140 micrometers area. So you know that in any fabrication industry, we will generally avoid usage of inductors, or we will minimize the number of inductors to a minimum value because they occupy more area, and you can substitute inductors with elements which are alternatives available to inductors. So generally, it is a practice to keep the number of inductors to minimum so that you can use the space for other components for